In this lesson, we look at another classical divide and conquer algorithm. The merge sort algorithm applies divide and conquer technique to the sorting problem to achieve better efficiencies than the sorting algorithms that we have already seen. The sorting problem, as you already know, is we are given an array of n elements, and the objective is to order or arrange the elements of the array so that they are in ascending order. Typically, let's say each element of the array is a number, then the smallest number should be in the first element of the array, and the largest number should be at the end of the array, and any number should be greater than or equal to its previous number in the array. That's the sorting problem. We've already looked at two sorting algorithms when we studied brute force algorithms, selection sort and bubble sort, and we know that both of them give an order n squared complexity. So if the array has n elements, in the worst case, the number of comparisons required to sort the array is of order n squared. So how can we do better than that? How do we apply divide and conquer to the sorting problem to obtain better efficiency than order n squared? That is what we will study in this lesson. The idea of merge sort is rather simple. We apply the divide and conquer idea literally to the sorting problem. So what do we do in divide and conquer? We divide larger problems into smaller problems. So if I am given an array to sort, can I divide it into smaller arrays, sort the smaller arrays, and then combine the solutions, right? So why not divide the array into smaller arrays? Till when should I do that? Well, if you divide it into a very small array, then the sorting problem becomes trivial. For example, if the array has just one element, then it's already sorted. There is no need to sort it again. If the array has only two elements, then sorting is either it's already sorted, or we simply swap or exchange the two elements of the array and it becomes sorted. So sorting a very small array of one or two elements is trivial. The only question is, how do I combine small sorted arrays to create larger sorted arrays? So this problem of combination, right, is called the problem of merging. How do we merge two sorted arrays? That is the basic thing we need to understand in the merge sort algorithm. The dividing part is simple. Sorting the smallest array is also simple. Combining two sorted arrays to obtain a larger sorted array is the basic problem that we need to study. Right? So the idea of merging two sorted arrays is like the idea of zipping two parts of a cloth together. Right? So here are, if you think of these as elements in one of the sorted array and these as elements in the other sorted array, when we zip them together, see what is happening. Right? The elements are ordered from left to right, one after the other. Right? Now, if we can zip two sorted arrays and obtain a single sorted array, I will get a sorted or merged array which is larger than the two smaller arrays. The only difference is when we zip, the elements of the two arrays get strictly alternate with each other. That may not be the case when we actually merge two sorted arrays. Right? But if you remember this idea of zipping together, that is the basic concept of merging two sorted arrays to obtain a larger array. Let's take an example. Right? So here I have two arrays. The first array is already sorted. It has 5 elements, 1 to 5, index 1 to 5, and the values are 5, 7, 11, 13, and 17. So these elements are already sorted in increasing order. The second array also has 5 elements in this case, and its elements 4, 8, 16, 32, and 64 are also sorted in increasing order. We are going to use an extra array, extra space, right? So I will use another array here in the middle which has 10 elements. That is enough, sufficient space to copy all those elements, and we are going to merge the first two arrays into this array of double the size, that is 10 elements. So how do I do that? Let's say I have a pointer I pointing to the first element of the first array and a pointer j pointing to, or an index, it doesn't have to be a pointer, an index pointing to the first element of the second array. I compare these two elements, 5 and 4 in this case. Whichever one is smaller, I copy that to the new array. So I will write 4 here because 4 is smaller than 5. And now we advance the pointer j or the index j to the next element. Right? I is not advanced. It stays there because that element was not copied. Now I compare this new element with the element pointed to by I. So I and j are now pointing to 5 and 8. I compare these two. In this case 5 happens to be smaller. So I will write 5 here and I will advance I to the new position. So now what do? We compare 7 which is pointed to by I and 8 which is pointed to by j. In this case 7 is smaller than 8, so I copy 7 here and I gets advanced to its next element, j stays where it was. So now we compare 8 with 11. Whichever one is smaller, in this case 8 is smaller, we copy 8 to the next element of the resulting array, and now we advance j to point to the next element. I remains at 11. So now we compare 16 and 11. 11 happens to be smaller, so we copy 11 there and we make I point to the next element. We compare 13 with 16. 13 is smaller, copy it, advance I to the fifth element now. Compare 16 and 17. 16 happens to be smaller, so copy 16 here and then advance j to point to the next element. Continuing this way, we compare 17 and 32. 17 is smaller, right? So j is now gone beyond the array. There's nothing else to copy from the first array. So 32 itself gets copied here, and then we have to advance j to the final one, which is 64. Right? In doing this, you might keep another index k pointing to the third array, just so that we know where to copy the resulting elements. So given this extra array, I was able to copy the elements of the given two arrays. The two arrays were already sorted, and the resulting array is also now completely sorted. This is the algorithm for merging. So you keep one index pointing to the first array, another index j pointing to the second array. Keep comparing the two values that are at I and j. Whichever one is smaller, copy that, advance that particular index. So you either advance I or j. In each case, we copy that element to the new array and we advance the pointer or the index into the new array. So by having this additional space, I am able to merge the given two arrays to obtain a larger array. Right? So this algorithm, if we write it in proper pseudocode, algorithm merge takes an array A and three things: low, mid, and high. Right? So let's see what these are. Instead of having two separate arrays, here we are assuming that the array A has two parts. Right? So here is from low to mid and mid plus 1 to high. This is the first sorted array. This is the second sorted array. The entire thing is not sorted. In our previous example, we had two separate arrays where the two pieces came. Here they are actually present in the same array A, one after the other. The idea is to merge them so that the entire array is sorted. And for doing that, we need extra space of the same length as A, from low to high, another array called B. How do we do this? So we keep a pointer h pointing to the first part of the array, a pointer I to the second part of the a pointer j to the second part of the array. I is going to point to the array B, where we are going to copy the elements. So while h less than or equal to mid and j less than or equal to high, that means while there are still elements in the first part and while there are still elements in the second part. H less than or equal to mid means h is going to be pointing somewhere here, j is going to be pointing somewhere here. They both should not go outside the bounds of those two parts of the array. So h should be less than or equal to mid, j should be less than or equal to high. What do? We compare AH and AJ. Compare the two elements. If AH is less than or equal to AJ, then we copy AH to BI. Right? The new array BI, where we are going to produce the merged array, and we advance the H pointer. Otherwise, we copy AJ. We copy the element from the second part to BI, and we advance the pointer J, the index J. In either case, we have written one element to B, so we advance the index of B. Right? This is all there is in the merge algorithm. This will work beautifully if both of them have the same number of elements, if both parts have the same number of elements, as was the case in our previous example. But that may not be true. What happens if one of the arrays is longer? We need to merge those extra elements as well. We need to bring those extra elements in. So to do that, if H greater than mid, that means we have gone beyond the first part of the array. First array is exhausted. That means there may still be some data elements left in the second array. So from J to I, all the remaining elements of the second array get copied to the new array BI. Right? Otherwise, the second array is exhausted. There may be extra elements left in the first part of the array. This part may be longer than the second part. So from H to mid, copy all those elements to the new array BI. Right? And then advance the pointer I on the index, on the array B. Finally, we don't want to leave the data elements in the array B, so we copy everything back. So to copy everything back from B to A, we simply go K from low to high, AK equals BK. So copy everything back to A. So we use the additional array to construct the merged array, and finally we copy it back to A, so that at the end the original array itself has the complete merged array. So this is only the merging part of the merge sort algorithm that we are looking at, because we already said if I am able to divide the array into small parts, I know how to sort very small parts. Now if I know how to merge two sorted arrays, I can construct larger sorted arrays. Let's look at an animation first. Right? This shows merge sort in action. The green parts are the parts that are getting sorted. So those are the parts which have been divided from the original problem of sorting this entire array. Right? And as they get sorted, the two sorted parts get merged. Right? Let me illustrate that in the next round when this animation runs again. So now we have two parts, they got merged. Now everything is sorted. So initially it was like this. Now this part is sorted, this part is sorted, they get merged now. Right? So they got merged. Now you have one part here, another part here, they will get merged now. Right? And that keeps happening, but the actual pieces that are getting sorted are the small ones. So you divide and divide the array into smaller and smaller parts, sort all the smallest parts, merge them together to finally sort the entire array. See how visually this looks different from bubble sort or selection sort that we have seen before. Here we are sorting smaller arrays and then merging sorted arrays into larger arrays. So the first half is sorted now. The second half is getting sorted. Right? 1/4 of it got sorted. Now the last fourth got sorted. Now this two parts. Now we have two halves sorted. They get merged to produce the entire array, sorted array. That's how merge sort works. So let's work out an actual example. Right? This is real world data, real data. I have taken Sachin Tendulkar's scores in the last 10 first class innings that he has played. These are his actual scores in the last 10 times he went into bat. So this is the set of numbers that we have. They are ordered reverse chronologically. This is his latest performance. This was 10 innings ago. And I want to sort these. Right? Suppose I know of a way to sort the first 5 elements of this. Right? Somehow I can obtain this sort. 140, 22, 56, 108 and 9 becomes 9, 22, 56, 108 and 140. And somehow I have a way of sorting the second 5 elements, right, into this. Now I can apply my merge algorithm on these two to finally obtain this array. Right? How does it work? So we compare 9 and 2, 2 is smaller, so 2 goes there. We compare 9 and 5, 5 is smaller, so 5 goes there. We compare 8 and 9, 8 goes there, 8 and 9, 8 goes there. So in this case, all these 4 elements came from the second array because all of them were smaller than the smallest element of the first array. Then we get 3 elements from the first array. Then 76 is smaller than 108, so we get 76 there, 108 and 140. So my merge algorithm can produce this provided I can sort arrays of length 5. So it's as though I'm saying I don't know how to sort an array of 10 elements, but if I know a way of sorting arrays of 5 elements, I can break the 10 element array into 2 5 element arrays, sort them, and then apply my merge algorithm to produce the final sorted array. So how does it work? If you look at this, first you are asked to sort the entire array. Let's say we have an algorithm called merge sort, right? That will be first called to sort from 1 to 10, the entire array from 1 to 10. What does it do? It doesn't know how to do that, so it's going to break that problem into 2 sub-problems. Sort 1 to 5 and sort 6 to 10. Right, so here is 1 to 5 and then 6 to 10. Once they are sorted, I know how to merge them. But how do I sort an array of 5 elements? I'm going to further divide it into sorting the array from 1 to 3 and from 4 to 5. Similarly, from 6 to 8 and then 9 to 10. Now, how do I sort an array from 1 to 3? I don't know how to do that. So I'm going to further divide that into 1 to 2 and then 3 to 3. Right? How do I sort 6 to 8? I don't know. So I'm going to divide that into 6 to 7 and then 8 to 8. How do I sort this array of from 1 to 2? I will divide that into 2 sub-problems. 1 to 1, 2 to 2. 3 to 3 is already there. This will get divided into 4 to 4 and 5 to 5. Similarly, this gets divided into 6 to 6 and 7 to 7. And this gets divided into 9 to 9 and 10 to 10. So now we have 10 sorting problems. Instead of 1, we have got 10 sorting problems where each array has only one element. 1 to 1, 2 to 2, 3 to 3 and so on. I know how to sort them. They're all already sorted. Right? All of these guys are already sorted. We don't need to sort them at all. There is no longer any sorting problem. I've just divided the sorting problem so much. There is no more sorting problem left. There is only a merging problem left. Right? How do I merge these two to obtain the sorted array here? How do I merge these two to obtain the sorted array there, and so on? So it's as though we have eliminated the sorting problem. We have reduced the sorting problem to a merging problem. Right? Because we divided the problem until each array had only one element. So the overall algorithm for merge sort itself is very straightforward, since we already understand how divide and conquer works. You're given an array A which goes from low to high. If low is less than high, that means there is more than one element. Right? It's not a small problem. If low equals high, there is only one element, so it is already sorted, nothing to be done. If it is not the case, if it is not a small problem, you compute the midpoint, where we take the, as always, we take the floor in case that's not an even number. So you do low plus high by 2 floor, that is the midpoint. Sort the first part, sort the second part, and merge them. Right? So recursive call to merge sort to sort from low to mid. Recursive calls to merge sort to start from mid plus 1 to high, and then we merge the 2 parts. So what happens in this merge sort? As we already saw in the tree of calls, this will again divide it into 2 smaller parts again and again until low becomes equal to high, in which case there is no sorting required. Then only merge will be called, and the merge will start merging those smaller pieces together to create the overall sorted array. So this itself is a straightforward implementation of merge sort, of divide and conquer. The only interesting part was in the merging part, which we already saw. So how long does it take for merge sort to run? to merge sort an array of size n, the time complexity is the time complexity of the two halves, namely merge sort of the first half and merge sort of the second half. So it's 2t n by 2 plus the cost of merging is n. It's actually linear in the size of the two arrays. So the cost of merging is n. So if we apply our substitution method as usual, this becomes 4t n by 4 plus 2n 8t n by 8 plus 8n, and as usual, if n is a power of 2, right, in the end you get k t 1 plus k into n. So k is log n. This is trivial, right? Sorry, this is actually n, not k. nt1 plus k into n. This factor is smaller. This is the larger one. So this is k is nothing but log n. So we have already done such analysis. So this will be n into log n, or we say merge sort's complexity is O log n. Right? So that's the number of steps involved in doing merge sort. This is much better than the n squared complexity that we had seen in the case of bubble sort and selection sort. So merge sort is a highly efficient sorting algorithm which applies the idea of divide and conquer to obtain n log n complexity for merge sort. Okay, so n log n is much better than n squared. So let's see a question here. What is the total number of times that data elements are copied in merge sort? So you are applying merge sort to an array of size n. Given the merge sort and merge algorithms that we have studied in this lesson, how many times do we copy the elements of the array? Is it n, 2n, n log n, or 2n log n? The correct answer is 2n log n. We're not talking about big O here. The actual number is what I'm talking about. So you see what happens is, if let's say m of n is the number of times that copying happens, right? It is nothing but 2m of n by 2. The number of times that merge sort copies in sorting an array of size n is 2 times the number of copies made in sorting each of the first halves, plus the actual copying that happens during merging. And during merging, it is 2n, because each element is copied from array A to array B once, and each element is at the end copied back from array B to array A. So every element is copied only once during the loop and only once at the end, but every element is copied. So there are 2n copying operations going on in each time merge is called for size n. So if you solve this, right, using the usual substitution method, it comes out to be 2 n log n. So it is not n log n or 2n or n, it's actually 2n log n. The important thing here is to include this term, because merge is not called only once. Merge is called each time merge sort is called recursively. So we must include this recurrence relation, and in the end it is not just 2n, it is 2n log n. Thank you.